We are doing the talk bilingual, right? Ciao, Michele.
Ciao. I'm going to turn my mic off.
Oh, nice to see you.
Yeah. Maybe you want to see some.
Yeah, how come Sweden doesn't have as many medals as Norway? I was thinking about that this morning.
All right, so I think we can go ahead and get started now. So hello, everyone. Welcome to this week's ENLA seminar. My name is Erin Carson at Charles University, and I'll be the one chairing the session today. So I'd like to welcome our speaker, Danielle Szyld, who is a professor of mathematics at Temple University. He's really a top expert in NLA and is really well known to everyone in the community. He's done groundbreaking work in particular areas of domain decomposition and also on asynchronous iterative methods, the latter of which will be the talk of his talk today. So he's currently the president of ILAS. He's the chair of the SIAM Committee on Section Activities. He is a SIAM representative to the Mathematical Council of the Americas, and he also serves on the editorial boards of a number of top journals in the field. So it's a pleasure to have him here as our speaker today. And Danielle, I'll turn it over to you.
Thank you. Hello, Mark. So this is the list of my collaborators in the last 5 years or so. Every one of whom contributed a piece of some sliding here. Eric Bowman from Sandia, my former postdoc Faisal UP, Edmond Chow from Georgia Tech, Mireille, who was a postdoc with me, she's in Quebec now, Andreas Frommer, Jose Garay, my former student, Christian Glusa, Frédéric Magoulet, and Ichitaro Yamazaki. So I will be talking about a new theorem on provable convergence rate for asynchronous method using randomized techniques. But before I do that, I want to tell you about restricted ID Schwarz methods and optimal Schwarz methods, asynchronous methods, show some numerical experiments, and then do some little philosophy about how we think of asynchronous methods and give you convergence results. I will stop at several points, as it's customary in this seminar. I want to thank the organizers for giving me this opportunity. I want to commend for a fantastic series of seminars. Let's just begin. So we want to solve a linear system of equations. Take a favorite system, which may or may not come from a PDE, but if it comes from a PDE, usually it's a discretization of some linear problem. So a 1 minute conversation about Schwarz methods. Classical Schwarz divide, you have a boundary, which as you see may not be smooth, and then you invent some artificial boundary conditions with overlap. That's the key to Schwarz methods, the overlap. So the red is the boundary from the left, and the blue is the boundary from the right. And if you have this boundary condition, as we do here, you can say, okay, I'm going to invent a boundary here and give some values and solve from the left, and that will give me values for the blue line, and I'll solve for the right. And I alternate, and Schwarz in 1870 proved that this converges to the solution, which means the overlap values are the same once you converge. This is what I just told you. Now, I showed this to you for 2 subdomains, but you could do any number of subdomains, and this converges. And over the last 20, 30 years, people have used this one sweep of this. So you go from domain 1 to domain Q, and they use this as a very good precondition for conjugate gradient method. Here's a sample of books on the topics. It's a very big topic. There are conferences every 18 months. The next one is in July in Prague, number 27, I believe. Now, algebraically, you can think of multiplicative Schwarz as block Gauss-Seidel with overlap. There's also something called additive Schwarz, in which instead of alternating, you just add the pieces. And as in the cases without overlap, of course, the iteration depends, the convergence depends on the spectral radius of the norm of the iteration operator. We'll use this later. So my 2 scientific brothers, Cy and Sarkis, invented something called restricted additive Schwarz, which means you solve your local problem with the overlap. Let's think that without the overlap, you have half of it, say half of the overlap on one side, half the overlap on the other side. You compute with the overlap, and then you throw away the information of the overlap and keep the information just without overlap. And that should to be actually more efficient. Algebraically, we can think of it this way. Now, AII is my submatrix corresponding to the overlap. I solve my usual block Jacobi. But if you do this and you iterate, this will not converge. And it will not converge because you are double counting the variables on the overlap. So people have put weights, did different things to make it converge, Richardson, etc. But restricted additive Schwarz does converge as a iterative method precisely because you don't double count, because you only keep the non-overlapping variables. So now you know restricted additive Schwarz. And I have 2 or 3 take-home messages. And the first one is that overlap pays off and in big way, and it comes almost for free because you are solving a slightly larger linear system, but it converges much faster. And as an aside that I will use later, alternative Schwarz, as I described, we can interpret this as a fixed point method. Let me explain. So I start with boundary conditions on the subdomain, which are not, they're in the artificial boundaries. They are not the true solution. And I iterate. And once I finish, I have new boundary conditions for the other subdomains. So essentially, I'm taking boundary values, I get new boundary values, and I iterate. When I get the fixed point, I converge because now I have the true boundary values, and that gives me the solution. Okay. Moving on, there's something called optimal Schwarz method. I told you that the iteration, the convergence depends on the spectral radius of a iteration operator. Okay, so if instead of putting Dirichlet conditions, I put some kind of Robin or Robin boundary conditions. Since these are boundaries that I invent, I can invent any boundary conditions I want. And if I do it this way, then I have a parameter alpha, and I can minimize, optimize the spectral radius of the operator depending on this alpha. That's called optimal Schwarz. Of course, you can do more. You can say, okay, instead of 1 parameter, let's do 2 parameters. This is called 0, this is called 2. The 0 and 2 corresponds to approximating the Dirichlet to Neumann map with the 0th order function or with the 2nd order function. And usually you can find these parameters in certain type of domains. All I'm saying here with this selected list of references is that many people have worked on optimized methods in different ways. Nowadays, you can do this more automatically and find the parameters in a reasonable way. And I explained this to you in terms of PDEs, but actually there is a algebraic version. You see, I told you that multiplicative Schwarz is blocked outside with overlap. The algebraic version of the optimize is the same way you change the boundary. You change a few entries in the overlap, and that's the algebraic version. And it turns out that this can be very extremely fast. So let me show you a picture from a paper which is 10 years old now. So this is 2 subdomains, but it doesn't matter. So the top line is non-overlapping block Jacobi, which we know it's slow. And the next line is overlapping. So this is the first message I gave you earlier that actually pays off with very little cost. And this line is when you pick the optimal value of the Robin parameter. You can converge in 2 steps. It's essentially a direct method. Or you can approximate a converge much faster than anything else. Okay. Any questions? Okay, so we have exascale machine coming, hundreds of thousands of processors. We as a community have been trying to figure out how to do things without communicating so much. And if you are doing Schwarz method the usual way with preconditioning, we have to do Krylov subspace methods. So normally we do Krylov, and then we do restricted to Schwarz or optimized restricted to Schwarz as a preconditioner for the Krylov method. And this will be prohibited because of the inner products. If you have hundreds of thousands of processors and you have distributed information, so it'll take a while. This was the 15-minute mark. Okay, so one idea is to essentially reverse the order. Because the outer method, your Schwarz method, and then you have your local problems, and you can do a Krylov method on your local problem, even with preconditioning. And the second idea is to do this in an asynchronous manner. What does it mean? So this is my local problem, and my local boundary conditions on my invented boundaries. And then my boundary conditions are coming from the, say, the left or the right subdomains, or if you have more subdomains, you have more of these. So I'm processor S for the S subdomain, and I take my boundary conditions, I solve, and then I produce an approximation that will give boundary conditions to the others. And the point here is that I don't want to wait for new information. When I'm ready to start, I start with whatever boundary conditions I have, even if it's the same as the previous information. And of course, at some point I have to stop, and there are techniques to do to satisfy stopping criteria, also in an asynchronous manner. You don't want to stop everything and say, okay, did I converge? Because you then incur in the communication bottleneck. From the algebraic point of view, it's essentially the same. I no longer have iteration counts. I say, okay, let me read all the information from the other processors, depending if it's shared memory or distributed memory. Anyway, I read it. I compute my right-hand side. I solve my local problem with whatever technique I use. And then if I'm using RAS, I restrict, and then I write the information. So this is my asynchronous, my philosophy of my asynchronous method. So there are no longer iteration counts because there is no synchronization. So one way people study this is, okay, I'm going to take my clock, my computer clock, and tag, in theory, the approximation with the clock when I write it. So when I write here, when I want to do an analysis of this, xj will be tagged with whatever I timestamp I wrote before. Okay. And my second take-home message is that asynchronous iterations actually work very well. And I'm going to show you a couple of experiments from relatively recent papers. So the first one considers the gravitational potential around the crater in Yucatan called the Chicxulub crater, created about 66 million years ago when there was this meteorite that presumably, or almost sure, helped decimate the dinosaurs. It's big, 180 kilometers diameter. And actually there's a lot of geological evidence for this. It's not an invention. So we do a finite element discretization of this pizza box, 250 kilometers by 250 kilometers by 15 kilometers high, on a graded finite element mesh. And we separate the subdomains in a parallelepiped way. This is our equation with data. This is part of the finite element mesh. We run this on an increasing number of degrees of freedom, 2.5 million, 20 million, 150 million on 250, 500, 1,000 processors, 168 processors. In this particular machine in France, half are one type and half of a different type. And we run the same code with optimal Schwarz, synchronous and asynchronous. And the smallest near system is about 4,000, so we shall solve it directly for this experiment. So here are the numbers, just to show that it works. So the top 3 experiments are with the 0 order approximation, the second are with the second order approximation. This is the number of iterations. This is the time. This is for the synchronous case. And this is for the asynchronous case. In the O0 here, we have about 20% of the time. Here is about 60% of the time in the best possible situation. Since there are no iterations, here is it should be new, the update, the minimum number of updates in each process and the maximum. We also have median, all the statistics. Since not all processors update the same number of times. Michele, who is looking over, asking, what about scaling? Well, it scales well, well enough. And here is a experiment using 2 levels from a year and a half ago. It was published. And this is a weak scanning experiment. If subdomain has 40,000 unknowns, and we solve using precondition Krylov method. We are talking here about 150 million variables again. So let's look at the timing here. The blue is the synchronous, and you can see it suffers tremendously from the communication, while the asynchronous is almost flat. And it scales well. It's very fast and it scales well. Okay, so let's do a little wrap up about half time. Overlap is worth considering for you. Asynchronous optimized Schwarz methods and 2-level RAS work well, they scale well. There's no communication bottleneck because there is no synchronization. Okay. Let's talk about some theory. Asynchronous method for fixed point problems. It has a long history. There are many, many papers. I would say at least 100 papers, but I put here a few that are more influential. There are a couple of books that are worth considering. In this book by Bahi and Computational Model and Couturier, there is the first, in my view, serious treatment of asynchronous stopping criteria. I wrote a survey for Y2K with Andreas Former for everything we knew up to then. Recently, Pierre Spiteri did another survey. A little different take, but a nice paper. But this, the theory for convergence is based on product spaces. You essentially, a block Jacobi type of thinking. So you have subdomains or subgroup of variables, each belonging to a space, and you have a product space, which gives you the whole vector. So it's essentially a block Jacobi operation. So if it's the synchronous version is inherently slow, then you do it faster by doing asynchronous, but it won't be earth-shattering. And this is why it kind of fell out of favor, I think. So why is it now different? In my view, it's different now because optimized Schwarz is fast, or it could be very fast. Also 2-level Schwarz. And therefore, when you do it asynchronously, it will also be fast. And that's why I believe it's worth considering. Okay. Any questions?
No questions in the chat.
Okay. So I want to share with you a philosophical way that I think is useful, which applies to asynchronous iterations, but it can also apply to other topics. So there are 3 ways, 3 types of models, or 3 types of realities, if you want. One is how the methods actually work in the hardware and the software. So when I say, I'm the local processors, I read the information, and then I compute, and then I write. In my use, I missed that there are actually details that you have to care. How do you do the writing in MPI? What does it mean? The hardware plays a role, even though we want to forget about it sometimes. But it does play a role. And in this paper in 2020, we dwell on some details of how to do things, or one way of doing things. And then you write or you think of a computational model like an algorithm, which is a model of what the computation does. It's not really the computation. It's just your computational model, and you may put some computational model hypothesis that you want to enforce, or you think you want to enforce. And then on top of that, is a mathematical model of the computational model, and that's the one you analyze. You're not analyzing what's going on in the hardware, you're analyzing your computational model. So it's good to keep the perspective. So I have a paper from a long time ago talking about these different models and many more with examples of different situations. So let's talk about the mathematical model. So this is what became a kind of standard way of thinking about synchronous iteration. Most of the reference I mentioned use this concept. So again, we have a time step, which is not an iteration number, but it is. Every time I tag an approximation, I increase my timestamp, which could be the clock timing. And then I have a set that tells me which blocks or which coordinates, which degrees of freedom, I update at this timestamp. And then I have the timestamps of what I'm reading. So if I'm the processor I read my other variables J, and when I read them, they come with a timestamp, and that SJ of K, which is the timestamp I will write my I when I finish. So this is, it takes a while to understand exactly what it is, but it's in the standard block Jacobi, you say, okay, xk is a function of the other k minus 1. Well, this replaces the k minus 1 because it could be k minus 2, k minus 3, k minus 20. And in order to analyze this, there are three assumptions. Again, this is the mathematical model of the computational model. One is that your tag has to come before your actual usage. You cannot use future information. That eventually what you read changes. It's not true that it will always read the same binary data. So for example, if a processor dies and there is no information, it's not taken into account in this situation. So when we talk about resilience, you have to think a little different model. And then that your local processor will not take forever to update. You will eventually update. So these are the three usual assumptions for your theorems in terms of your mathematical model of the asynchronous iterations. And then you write your mathematical model in this way. You say, okay, at the timestamp k, I either completed my fixed point iteration or I didn't. If I didn't, my update stays the same. If I did, that changes. And again, we have a product space. Each of these are the components of the product space. And this is we call this an asynchronous iteration with the strategy IK. And the difference between my current timestamp and the timestamp of the variables I read is called a delay, just the difference. If every delay is 1, you're just doing block Jacobi, say. So there are different models and different theorems. Some theorem says, okay, I'm going to assume that my delays are bounded, that there is a maximum delay. And I call that D, that it cannot be older than, say, 20 steps or 55 steps, whatever. And with these assumptions, then people have proved theorems. And these are two that I like very much. And one can paraphrase and say, okay, this is your standard fixed point iteration, which could be multiplicative Schwarz, okay? If you have some operator norm, not any operator norm has to be conformal with the product space, and the three typical assumptions, then this will converge to a unique fixed point, which is your solution. Okay, notice that I only think that it converges. I cannot tell you how fast it converges. Again, there are no iteration counts. They are just timestamps. And for many people, this is a problem. Often I would give a talk about asynchronous Schwarz, and my scientific brother, Tsai, would say, Daniel, what is the convergence rate? Is it h squared? Is it h? Is it, well, we know it's linear. Well, we think it's linear. Some other theorems, instead of the norm, they ask for the spectacles of the absolute value of the operator. But same idea. And we have used these theorems to show convergence on the experiments I show you. So we know if we have a theory of convergence, we think it's convergence, but we don't have a convergence rate. Okay. If there are no questions, I will go to the randomized view of asynchronous Schwarz. So 20 years ago, Striquerda published a paper in the LAA. This is a very seldom referred paper. And John said, okay, I'm going to interpret my asynchronous iterations in a probability sense. And there are a lot of things that happen that at any moment K, either I finish or I don't. And I would say, okay, this has a probability to be survived. He also considered the delays or the timestamps as random variables. So he set up this probabilistic view of asynchronous iterations. And he was able to prove that for the linear case, just if you have a linear system, for a convergence operator, then the expected value of the error will go to 0, which we knew in the usual sense, but he showed it in the probabilistic sense. Furthermore, he was able to give a rate of convergence for this in a linear manner. Again, K here is not the iteration number, it's the timestamp. And this number R, it's a little hard to get a hold of. Precisely, it's the radius of analyticity of a matrix, which includes your operator, includes the random variables for the timestamp, it includes the probability, and you get all this together, and this is, and then you figure out what is the radius analyticity of this function, and this is the number that goes here. Which may not be important if you all want to show that in the probabilistic sense, there is a linear convergence rate, and there is such a number. Anyway, the paper is there, and I think it's an important milestone, even though people haven't thought about it much, I think. And I want to repeat This is the same asynchronous iterations that we've been talking about all along, just that we analyze this with the probability mindset. Okay, we say, okay, we have as I explained earlier, the computation, we have the actual computation, the computational model, and this is a mathematical way of analyzing the computational model. It's not that it's a new algorithm. Okay, clear? All right. Now, in 2014, Chaim Abron and his co-workers at IBM, Chaim is speaking next week, in 2 weeks, next version of this seminar, by the way. He won't be talking about this. He talked about randomized preconditionals, but they presented this at the conference and then published a paper at the Journal of HCM for the specific case of a symmetric positive definite matrix. And they take essentially the same idea, but now they say, well, I can implement this. I can set up probabilities and do so this is my block. This is, okay, first of all, they did it for point Jacobi, not block. Now, randomized Jacobi, in my view, is exactly the same as randomized Gauss-Seidel, meaning you do one relaxation on a row, and then the next time you do another relaxation. Okay, that's your randomized Jacobi, but you can also think of randomized Gauss-Seidel because you use the information that you already computed, so it's the same thing. And in the randomized literature, they call it randomized Gauss-Seidel. I should say that in, and maybe you say, and others will correct me, most of the work in randomized NLA is for rectangular matrices. There is very little work on square non-singular matrices. One exception is a recent paper, which is not even out yet, not even reviewed yet, by Nathan Kasutasa and Trop. But in general, this is mostly done for low rank. Here we're talking about a square matrix. And so we do block, when they do point Jacobi, or point Gauss-Seidel, if you point Jacobi, this is the Jacobi operator. Chat question. Catch markers, yes. Yes, there's a lot of work on catch markers. Yes, but that's a different kind of speech. I agree. I know that word. Good. Okay, so here is the same thing we're doing. So you have my Jacobi matrix, Jacobi operator, and this is one relaxation. And they say, okay, I'm going to take the ith row with probability p sub I and do update it, and the others I keep the same. I want to emphasize this is exactly the same as we have in this situation. Okay, so this is this paper, and for the symmetric positive definite case. And now, what is the computational model? They use bounded delays, and they use what's called atomic rights. Every time step, I can only update one component. Of course, when you implement this, you have to make sure that it's how it's implemented. And they do an analysis, and here is a theorem. This is their theorem in the notation I just showed you. So this is your Jacobi operator, and they use the infinite norm, the max norm, and they say if it's not huge, or if you want, given a fixed A, if the delay is not too large, so that this holds, then the expected value of the A norm of the error is bounded by this quantity. So this is the relative error. Again, we have a a factor, and we have a convergence rate, which is linear with some parameters here. These functions, they're complicated. I didn't think it was educational to show them here, but they depend on the maximum Jacobi eigenvalue, the delay, the size of the matrix, the norm, the condition number, and then they have this. Okay, so this is for full disclosure. So this is the result. So it's the first and this is more well known. There are many more people citing this work. And they use, as a summarized, provable linear convergence. So Tsai would be happy using the A norm and the probability with a uniform distribution. And Andreas Romer and I said, okay, can we do the same for non-symmetric matrices? What kind of matrices? What norm do we use? Here is the A norm. If you have a non-symmetric or non-positive definite, you have to think of the 2 norm or some other norm. Let me mention that Convergence and Sosonkina, they have a couple of papers doing experiments with this version of asynchronous methods. They say, okay, why do I have to use uniform distribution? And they show that they can get maybe 20% better if they do Gaussian or if they do exponential distribution. As another comment on the literature, there's an old paper by Krylov that many of you know on algebraic Schwarz, but this is a newer paper from 10 years ago. And they consider the same SPDE using the A norm, okay? And they use randomized Schwarz methods. And they show similar, not similar, but they show convergence and convergence rates using the expected value of the error in the A norm in the same way as Abram and collaborators. But this is not asynchronous, this is randomized Schwarz. But it's so both Abram's paper and Gupta and Krylov were both inspiration and challenges for us to say, okay, this can be done. We should be able to do something for non-symmetric A. And I think we did. So let me give you some background information. So you have your matrix, you have a set of variables, n variables, and you partition it into blocks. And you can take, so you partition and permute your set of, to get your block. And then if you do the same with the identity, you get rectangular matrices S sub I. And if you put them together, this is what in the randomized NLA literature is called a complete sketching. So each of these rectangular columns, they call it sketching. And it's a complete sketching if this matrix is not singular. So in this case, it's a unitary matrix. And then this partition gives you a partition of your matrix into blocks, Aij. And we want to assume that we can do block Jacobi with no problem, so that the local subdomain gives you a non-singular matrix. And in this situation, François Robert in 1969 has a long paper in LAA on block H matrices. And he defines the matrix to be block diagonal dominant. In this case, I write it by columns. You can also do by rows. If this quantity is less than 1 for every column. This is equivalent, as you can see, that your block Jacobi matrix is has columns that some are less than 1 in this form. Okay. As a side remark, this concept of block diagonal dominant was used recently in 2 papers, one by Michele Benzi and collaborators for analyzing block Monte Carlo methods the successful way. And Echeverria, Liz, and Nauden use this to get new type of Kerckhoff circles and also estimates for inverses for the elements of the inverse. Yes, J is not equal to 1 because it does. So someone asked Jim, then you don't have to get I different than J. My matrix, so yes, for this concept, you get J different I, correct. I don't worry about this because, yes, you have J different than I, correct. Sorry about that. When I think of the Jacobi matrix, the diagonal blocks are 0, so I don't worry about that. But in this case, you're right. Thank you, Jim. Okay. So new definitions here, J different I would generalize this the same way there is a generalized diagonal dominant concept. We generalize this to block matrices. So you have a positive vector U. In this case, U is real. The matrix could be complex, but U is real and positive of the size of the number of blocks. And you want this to be less than 1. Instead of all U's to be 1, U could be something else. And if you have the block Jacobi matrix, we invent a new norm, a new operator norm, which depends on your sketching and on your vector U, which is the maximum of the column sums weighted by U. Now, this is not an invention out of the blue. It's the operator norm induced by this vector norm. So you take your vector, you sketch each part, you weight it with U, and add up, this is a weighted max norm. I didn't write it down, but there's a lot of freedom of choosing which norm you want to use in this subdomain. You can use a norm appropriate for each subdomain. It could be the 1 norm, the 2 norm, the infinity norm. It could be the same for all subdomains, different ones. As long as you specify it, this works. And then the norm Hij is the standard operator, is the maximum Hij Vj divided by the norm. So it's a mixture of the I norm in the subdomain I and the J norm in the subdomain J. Everything is consistent. So we have this new norm, if you want. So this is our new result. Fix a permutation and partition, get your sketching matrix, get a U vector positive, and take a matrix that is generalized for block dominant in the sense of block with respect to this partition and this U. And then take your block Jacobi matrix. You see this should be B, not A, B inverse B. So the block diagonals are 0. So you have this precondition residual, if you want. and take this new norm and take these column sums. And we define this convergence factor that depends on the probabilities. The expected value of the precondition residual in this new special norm has a linear factor of convergence. And the exponent here is your timestamp divided by the delay. And if you think of this alpha, well, 1 minus alpha, and here I have 1 minus rho. So alpha is like an upper bound for alpha is this norm. So if this norm is less than 1, then this number is less than 1. And we have the convergence rate for block Jacobi method. And we have this for block Jacobi asynchronous iteration. Very good. So this is our new result, one of our new results. So short conclusion, synchronous iterations work. As we saw, they can be very fast, especially with overlap. And after 4 years, we have now a provable linear convergence rate for a large class of matrices. And eventually this will be written up and be on my website. Thank you very much.
All right, great. Thank you, Danielle, for the wonderful talk. We did have some questions in the chat. Ilsa, do you want to go ahead and unmute?
Yes, I just wanted to know, you said that there's a difference between randomized and asynchronous. And when you showed that result from Strickwerder from 2002,
Yeah.
Asynchronous iterations, one could think of that as Bernoulli sampling. You know, you sample each coordinate with probability P, and you don't sample it with probability Y.
I want to formulate my answer in an intelligent manner, hopefully. You can set up randomized without being asynchronous. Asynchronous has to do with not waiting for anything else. So what Strickwerder did is he interpreted the asynchronous iteration as a randomized process. You can have randomized iterations, randomized processes which are not asynchronous. In fact, nothing that I've seen in the randomized literature thinks of asynchronous iterations. But the asynchronous iterations, they do exist, they work. They are kind of strange for many people, partly because without knowing it, they are randomized in the sense that you may not get the same answer at every time because there are the way the processors work, the way they have to wait or not wait, different things. So you don't get the same answer necessarily. I mean, you converge, but your iteration may not be exactly the same when you stop, because also it's hard to stop at the same time every iteration. So one new concept, if you want, or different concept, is to think of the asynchronous iteration as a random process. So that's what Strickwerder did first. He said, okay, randomized are strange, but they're not that strange. Anyway, I hope I answered your question. I see here, Michele asked, tell something about swapping criteria. Yes. So suppose you have whatever, 100 processors. Then you can compute your local residual. Of course, the local residual doesn't tell you that the global residual is converged. And normally you say, okay, I converged. So I send a message, I converged. And everyone, when they converge, they send a message. And asynchronously, this propagates through the system. And when everyone converges, they say, okay, now is a good time to check that everyone converged. And what Bahia and the people said, and what Magulesi is using too, is say, okay, this is true, but I don't trust it. Let me do twice this, make sure there are two sweeps. First, everyone converged, then a second time everyone converged and say, okay, we converged. In the paper in 2020 with Blue Sabom and my co-authors, there are several experiments in which when we compare synchronous with asynchronous, the asynchronous achieves a lower true residual norm at convergence because we do more work. I mean, some converge, some didn't, and then at the end, by the time the stopping criteria get satisfied, you did more work. And that's a consequence of not stopping to check, so to say. I hope I answered your question, but I'm open to more questions.
Yes, any other, yes, Volker?
Yes, thanks, Daniel, for the nice presentation and giving some illumination. Has somebody done a statistical analysis of this? I mean, in a certain way, one would say, if you do this anyway, in this asynchronous way, one should maybe do a statistic running the same thing 100 times and then getting some kind of probability that tells you how good, with what probability the asynchronous iteration after so many steps gets you a reasonable result. I mean, like you would do in a randomized algorithm, you want to also get a probability that you get the correct result.
I don't know if anyone hasn't done this.
But I mean, Ranka in his early work assumed bounded delays, right?
Yes.
And then you could get results bounds. But I think if you view this asynchronous iteration, that Strickwerder one, as Bernoulli sampling, you should be able to get what Volker wants. Each coordinate is sampled either with probability pi or not sampled. And I think if you view it that way, you should be able to get something.
Thanks.
But let me say something about the bounded delays. When you program this, there is no restriction on the delays. You just assume that they're going to be bounded. It's just an assumption.
They enter in your matrix, right? That matrix that you had that had the diagonal, the P with the PIs on the diagonal, that means if some of the PIs are really small, that matrix is really ill-conditioned, and then that spectral radius will be huge, right?
Right, but that's not the that matrix is not an operator matrix. That matrix was only used to compute the radius of analyticity for the convergence. Strickwerder's work mostly works with integral formulation of the probabilities. So it's different, so to say, analysis that were I'm used to. But that's how he works and comes up with the result.
Can I ask another question?
Yes, please.
So in your theorem that you showed us at the end, how practical it is to check the conditions? You have this vector U, for instance.
Yes, okay. I'll answer in a second. So what we need is that this weighted max norm in the block sense is less than 1. So so the same as in the point case. In the point case, this is a generalized block diagonal dominant. So if you have an H matrix, you have a Perron vector who gives you this U. As you know from your paper, there are algorithms to check the matrix is block diagonal. Well, the paper that you use is for point diagonal, not block diagonal, but it can be generalized to blocks very easily. Okay. So there are matrices from applications and generally that there is a natural way of having these vectors U, and therefore it's easy to check if the matrix is convergence with this operator or not. For other cases, well, first of all, you can check for U equal 1, and if it doesn't work, you have to think, okay, is there a U that makes sense to try?
All right, well, I think, is there another, we have time for maybe one more question.
Last question. Very interesting talk, Daniel, but I'm puzzled by your motivational example, because that's a potential problem. You just can solve it just computing integral.
I'm not. These are experiments with that they were meant to show that the asynchronous methods make sense. These asynchronous methods, and in general, all these Schwarz methods can be applied to many problems. We just haven't run other experiments. These are the first experiments to make sure things make sense. I'm not saying if you have a potential problem, do this. No, this is just an illustration. This can be used and have been used for many problems.
Okay, thanks.
All right, so I think we're out of time for today. So thank you again, Danielle, for an excellent talk.
Thank you.
And just to advertise our talk next week, we hope everyone will join us again in 2 weeks for the talk of Chaim Avron, who will be speaking about randomized